We're going to look at the topic magnetic fields. Welcome guys for this particular tutorial. We're going to look at magnetic fields and we're going to discuss what are the key areas, the key concepts that you need to understand in this particular topic. On my table, I have past paper questions. I can see I'm having, let me just show you guys what I'm having here. I'm having oscillations and simple harmonic motion booklets. I have electric field booklets. I also have temperature and thermodynamics. There is also capacitance here with me. And I also have the year 13 physics book A. So book B will be having quantum physics, but book A is usually having circular motion. And then we are having there, just position it properly, we have circular motion. Then after circular motion we have gravitational fields. That's what's in book A. We have also the concept of temperature, thermal energy and equilibrium. So that is the part that we are having. Then we have the concept of, this is internal energy. Yes, of course. Yeah, internal energy we discussed, and you can be able to check some of the tutorials that we did in this particular video regarding that. And then we have now oscillations, whereby we defined what an oscillation is and different examples of oscillations, which are well displayed here. Then we also talked about the terms used to describe oscillations. So those are the concepts that already we've discussed here, and you can be able to check the link in the description. It will take you straight to that. So we have also energy in simple harmonic motion, then damping motion, and then the last part is actually resonance. Yeah, resonance. Then we move to electrical field. That's in book 1. And then we talk effect of uniform electric fields in motion of charged particles, well discussed. And then we have electric force between point charges, and that is actually linking Coulomb's law that states electric force between point charges directly proportional to the product of the charges and inversely proportional to the square of the distance of separation. Yeah, so basically that's what book 1 entails. Then we moved now into capacitance, whereby we defined what capacitance is, and then energy stored in the capacitors. Then once we finish that, now in A-level physics, you need to understand about the concept of magnetic fields. Yes, magnetic fields, another area that is very, very key. You need to understand magnetic fields which are created in a loop, magnetic fields created in a solenoid, and some of the key factors that you need to remember there is that at the central axis, the coil is having uniform magnetic field. Yes, uniform magnetic fields. So make a magnetic field at this point and this point along the axis of the solenoid is basically the same. And at the outer region, the magnetic fields are weaker because you can be able to see that is separated by the lines have a larger distance between each other. Next is the force on current carrying conductor. If the conductor is in a magnetic field, then it means it's going to experience a force, and you can be able to predict the direction of the force using Fleming's left hand rule. I'm using my left hand. So the first finger points the direction of the field, current, and the thumb shows the direction of motion. Okay, so magnetic flux density is defined as force per unit length acting on a long straight conductor carrying a unit current which is placed in a magnetic field perpendicularly. Next, a concept that you really ought to understand is the concept of deflection tube. And remember this, whenever an electron or a charged object is placed within the magnetic field, it's going to experience a force, and this force can be able to be determined by Fleming's left hand rule. Because electrons are moving in this direction, then you have to turn your current finger to face backward, because usually current and electrons are in opposite directions. So I hope that is a concept also you really ought to remember. There's the concept of velocity selection. Now, velocity selection is used in a velocity selector, whereby only particles with a particular velocity are going to pass. So we understand that if an electron is placed in a magnetic field, in an electric field, this electron is going to experience a force. Yes, let's say that we have a negatively charged electron. If it's placed in the magnetic field, it's going to experience a force, and it's going to be attracted to the positive plates. But within here, we also have magnetic fields which are acting into the page. So whenever you have also magnetic field, a charged object or a charged particle is going to experience a force. So meaning that if this experiences a force upward and we introduce magnetic field, it will experience a force downward. Now, when the two forces are equal, magnetic field and the electric field forces are equal, then it means that the charge, because electric field is given, the force due to the electric field is given by charge times E, and the force due to the magnetic field is given by magnetic flux density times the charge times the speed at which it's moving. So if they are equal, you can see we can be able to cancel Q and Q, and then we're going to remain with V. B is equals to E. So if we divide by B both sides, we shall have a particular velocity where this which this particular object can be able to pass and deviated. It's not going to be pulled upward or downward, because the two forces are balanced. So under velocity selection, you need to understand that that's used in spectrometer, and also is used in accelerating tubes. And then we have the concept of Hall effect. Hall effect is the production of PD. Look at a scenario whereby current is passing through from this end to this end. Yes, and if this conductor is placed in a magnetic field, it means that the magnetic fields are going to exert a force on the charge carriers. So the charge carriers are going to be deflected, are going to be drifted. So if the charge carriers are drifted, one side you'll have charges of the same sign, and the other end you are going to have charges of the same sign. So you will end up having the charges separated. And when charges are separated, we are going to have a potential difference between these two plates. That's basically what we are going to talk about. So Hall voltage is going to be given. If you want to calculate what's the value or the size of the Hall voltage, it's going to be the magnetic flux density times the current that is flowing, divided by the number density, number density of the charge carriers times the thickness. And the thickness we're talking about is the thickness where the magnetic fields are acting, not this distance, guys. Is this particular thickness that we are having here, where the magnetic fields are acting into. So you need to get this very, very clear, guys. Then we're going to have a derivation of that particular formula. How is it derived? And that is exactly what I did in this particular video. And if you want to access this PDF, you just check the link in the description so that you can be able to go to our Patreon page, so that you can be able to download this particular notes, so that you can be able to access them and then continue. Then The last bit is forces. Second last is the forces between parallel carrying conductors. So if we have two conductors which are parallel and they are carrying current, then we are going to have a force exerted between those two particular conductors. You need to remember this. The force acting on this conductor will be due to the magnetic field of this other conductor, because the two wires are sitting in the magnetic fields of the other. So for instance, let's look at this scenario here. We have two wires, guys. Wire 1 where current is going into the page, and wire 2 where current is coming out of the page. So if we want to predict the direction of the magnetic fields due to wire 1, we are going to point the thumb. This field is going in which direction? I have to change this. The fields are going in which particular direction? The fields are going into the page. So you are going to use right hand grip rule. Yeah. Assume you are gripping this conductor using your right hand, the thumb pointing inwards. Yeah. So the fingers will carry around the conductor. You see that? Yeah. So this is the direction in which the fields are going. So the fields will be in that particular direction. So upon looking at that, then we can be able to say that one of the field will go and will be cutting through this second conductor. Then the field will be pointing down tangentially like that. Yeah. Like that. So meaning the magnetic field will be downwards, the current is going inward. Then we can be able to predict the direction of the current using Fleming's left hand rule. Yeah, you hold your fingers at right angles like that. Yes, such that the first finger points the direction of the field. So my direction of the field is downward. So I'll press the finger like that, field, and the current should be in. So let me just repeat this. This is the field. Should be pointing. Current is out of the page, guys. The current is out of the page. So the field is downward. The current is getting out. Yeah, this one here. The current is getting out, and then the force is in that particular direction. So if you just hold like that, yeah, fields, currents out of the page, and then this term is pointing in that particular direction, indicating the force in that direction. So wire 2 will experience a magnetic force due to the magnetic field of wire 1, and wire 1 will experience a magnetic force due to the field of wire 2. So you realize that if current is flowing in opposite direction, the fields, the wires are going to experience a repulsive force. But if the current is flowing in the same direction, the wires will experience an attractive force. The next area, the next concept is the concept of electromagnetic induction. And you need to understand that electromagnetic induction is a process through which electricity is generated when there is a magnetic flux linkage. So we are having a magnet. If you have a magnet and you bring it closer to the coil, these fields are going to cut through the coil. And when that happens, when there is a magnetic flux change, linkage, or there is a change in magnetic flux, then we are going to have induced EMF in the coil. And what's the origin of this electric current when there is a change in magnetic flux? Guys, we have mentioned that in the previous section here, that if we have a charge moving in a magnetic field, it's going to experience a force. We have mentioned that, and you did not question. And that force is equivalent to the magnetic flux density times the amount of the charge times the speed at which that particular charge is moving. So if the charge is stationary, it means it's not going to experience any amount of force. So we accept at this point that when there is a charge moving in a magnetic field, it's going to experience a force. Now here we are talking about electromagnetic induction. When you move a conductor within a magnetic field, remember inside the conductor we have charges, we have electrons. So those electrons are going to experience a force due to the change of the magnetic flux. And that is the origin of the current in electromagnetic induction. So in this topic, you need to understand that the direction of induced current is going to be determined by Fleming's Fleming's right-hand rule. But before that, you need to understand the concept of Faraday's law. What does Mr. Faraday say? Mr. Faraday says that the amount or the magnitude of induced EMF is directly proportional to the rate of magnetic flux linkage. Rate of change of magnetic flux linkage. So meaning that if you move this magnet faster, there will be a large amount of induced EMF because the rate of change was high. If you want to increase the amount of EMF induced, use more turns. Yeah, use stronger magnet, stronger fields. Now, without wasting time, let's talk about magnetic flux density. And the magnetic flux density can be defined as the force acting per unit length, acting along conductor carrying a unit current within a magnetic field. So if you're going to be asked a situation whereby you are expected to work out the magnetic field, magnetic flux density, you are going to say force over current times the length. And if in the event you are being asked to calculate the magnetic flux, you are going to say magnetic flux is equal to the magnetic flux density times the area. And the area we are talking about is the area which is perpendicular to the field. So in the event there is an angle, the magnetic fields are making an angle. The magnetic fields are making an angle with the area. Then the angle that we are talking about is the angle between the normal of the area and the magnetic field. So which means that magnetic fields at an angle will be BA, magnetic flux density, times the cross-section area times cos theta at that given point, times cos theta, guys. But if the magnetic fields are parallel to the area, if the magnetic fields are parallel like that, they are just passing across like this, they are not crossing that particular area, then there will be no magnetic flux there. The concept of magnetic flux linkage, once you have gotten the magnetic flux, then if you are working out the magnetic flux linkage, take the magnetic flux that you have gotten times the number of turns or the number of coils, because the magnetic flux will represent for 1 turn. So if you have 1,000 turns, you'll say burn the magnetic flux density times the cross-section area, and this particular part here is giving you the magnetic flux density, magnetic flux. But if you are finding the magnetic flux linkage total, that's going to be magnetic flux times the number of turns, or the magnetic flux density times the area times the number of turns. But if they're making an angle, you have to say that is cos what? Theta. Now, rate of change, that's where we have the concept of what? The concept of Faraday's law. Yeah, which is basically used to tell us the amount of induced EMF is directly proportional to the rate of change of magnetic flux linkage. And induced EMF is equal to N change in magnetic flux Then the negative sign is basically Lenz's law, which is trying to tell you that the induced EMF in such a way that it tries to oppose the change causing it. So if the magnetic flux, for instance, let me just show you here. If you work out the gradient here, and if the gradient is positive, the rate of change of the magnetic flux density, then you are going to say the gradient is positive, then the EMF induced is going to be negative. But if the gradient is 0, it means there is no change in the magnetic flux density, then it means that there is no induced EMF. But if the gradient is negative, then it means we're going to have a positive EMF induced. The negative sign means if the gradient is negative, the induced EMF is going to be positive. Now, having understood about Faraday's law, and Faraday's law, I've said, is it tries to give us how do we get the induced EMF. Now, for you to get the induced EMF, you need to do the rate of change of magnetic flux linkage. And once you have that, that will be equivalent to the induced EMF. We have Lenz's law, and Lenz's law is trying to tell us the direction of the magnetic field. Sorry, Lenz's law is trying to tell us the direction of the induced EMF. So the direction of induced EMF is such that it is flowing in a direction where it's flowing in a direction such that it creates magnetic fields which oppose the change causing it. Now, look at a scenario whereby we have a coil that is being held stationary, and then we have a bar magnet, and a north pole is being pushed into the coil. So remember, we have said that if the magnetic field cuts through the coil, we are going to have the induced EMF. And if there is induced EMF here, it means that the direction at which the induced EMF will be flowing in this coil is going to be flowing in such a way that it creates a north pole in this end. When the magnet is trying to approach, it will be having a north pole here. And if a current is induced in the coil due to the change of magnetic flux, then the current in the coil will flow in such a way that it's going to create a north pole at this coil, so that you will have to do work for you to push or to force the coil in. And this is under the concept of the law of conservation of energy. Energy cannot be created or destroyed, because when you are pushing the coil, the magnet in, due to the repulsive forces, you are doing work. You are doing mechanical work. Then that mechanical work that you are doing is converted to electrical energy that is running inside this particular coil. So Lenz's law is trying to tell us the direction of induced EMF, but Faraday's law is trying to give us how do we the way we can be able to get this particular induced EMF. So in the event we are having two coils like that here, so in this particular setup we are having a DC current running around, and when DC current flow in this coil, it's going to create a magnetic field. These magnetic fields which have been created are going to cut across this coil here, and then there will be an induced EMF in this particular coil. But the direction in which the induced EMF will flow here, it will be in a direction in such a way that it's going to create a pole that opposes this, and then we are going to have a repulsive forces between those particular two coils. So you need to have a solid understanding in this particular area, so that anytime you are going to be asked questions from this particular topic, you'll be in a position to answer. we shall be having later we shall be having a solid discussion. You need to check in the description if you are watching this video later. I have already done the concept. I've already done a video on this particular worksheet of magnetic field. You can be able to access it in our video here, just in our link. Check the link in the description so that you can be able to know how do you define the term magnetic flux density. One of the questions that was asked in recent years: how do you draw magnetic fields around a conductor? This question may seem very simple, but some guys and some funny students will get it wrong. You need to understand that the fields are concentric, but as you are moving away from the conductor, the distance of separation of the field is going to be increasing, because as you move away from the field, you're going to have the fact that you need to accept the fact that the magnetic fields becomes weaker. So also I've discussed about force experienced by two conductors carrying current, and now you are being explained, you are being told, explain, the examiner is telling you, explain why two wires exert a magnetic force on each other. So we have already mentioned in our discussion that the two wires are producing magnetic fields, and each of the wires is sitting on the magnetic field of the other. So there's going to be a force well demarcated there. And also we are going to look at, you'll see Faraday's law, how it's set and how you can be able to apply that. Guys, if you're new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. So guys, so I've basically ideally taken you through this particular topic, and if you've gotten value on how you can be able to handle most of the concepts in this particular tutorial, consider checking out my Patreon page and also support it, guys, so that I can be able to keep on doing more content as far as Proflan content of A-level pure math and physics is concerned. All right, so I think we can stop there. And if you can be able to check through the notes, you can download them in our Patreon page. If you have any question, guys, you can reach me out. You can check out our TikTok account, Proflan Academy. Proflan in TikTok. Can leave a message direct to me, so that if there is any area that you want me to work on, you can be able to get it for me, guys. I wish you all the best for those who are going to sit for their exams. I wish you the best of luck. Please don't forget to subscribe, like this video, and also leave a comment down below.